Hi everyone, I am Dr. Kumar, Assistant Professor, Department of Chemistry, School of Basic and Applied Sciences, Maharaja Agar Sen University, Baddi. Today I will talk about basics of solid state chemistry. These are the contents. First is introduction. In introduction, we will speak about solid state, types of solid state and their characteristics. Then we will discuss some basic parameter, some basic parameters like faces, edges and interfacial angle. Then crystal system and their types. After that 14 Brebbius lattice, crystal symmetry, and then designation of planes, diffraction of X-ray by crystal, and last Bragg equations. As we all know, matter is made up of solid, liquid and gases. Out of these three, which state exists depends upon two main factors. One is thermal energy and second is intermolecular forces of attraction. In case of solid, the intermolecular forces of attraction are very large as compared to their thermal energy. But in case of gas, the intermolecular forces of attraction are very weak. Due to strong intermolecular forces of attraction, solids are rigid and have definite shape compared to liquid and gases. In classification of solids are divided into two main types, that is amorphous solid and crystalline solid. In crystalline solids, the constituent particles are arranged in a definite and regular patterns. But in amorphous solids, the particles are arranged in irregular way. Crystalline solids are anisotropic in nature. Anisotropic means they have different properties in different directions. While amorphous solids are they are isotropic in nature. Crystalline solid further divided into four types, that is covalent solids, metallic solids, ionic solids and molecular solids. In covalent solids, the atoms are joined together by strong covalent forces. In metallic solids, the atoms are held together by metallic bonds. In ionic solids, the ions are held together by strong electrostatic force of attraction. And last is molecular solid. The molecular solid is further divided into three categories. First is polar solid. The example of polar solid is solid SO2. Then non-polar solid I2, and then hydrogen bonded solid. Example of hydrogen bonded solid is solid ice. Before discussing the symmetry of the crystal and their types, there are few basic terms which are related to it, that is faces, edges and interfacial angle. So what is faces? Faces are every crystal are made up of parallel surfaces. These parallel surfaces are known as faces, and the edges are formed by the intersection of two faces. For example, a cube has 6 faces and 12 edges. And last is interfacial angle. It is an angle between two adjacent sides of a faces. Crystal system. There are 7 crystal system, and crystal system is divided on the basis of interfacial angle and their edge length is. So first is cubic crystal system, then tetragonal, then monoclinic, orthorhombic, triclinic and hexagonal, and last is trigonal crystal system. Out of these 7 crystal system, cubic is most symmetrical and triclinic is least symmetrical. In cubic crystal system, all sides are equal and all angles alpha, beta, gamma is equal to 90 degrees. They are also equal. On the basis of primitive and non-primitive unit cell, these 7 crystal systems are further divided into 14 Brebbius lattices. First is primitive unit cell. In primitive unit cell, constituent particles are arranged at the corner of the unit cell. While in non-primitive unit cell, the constituent particles are placed on the corner of the unit cell and some specific positions. First is cubic. In cubic, we have three type of unit cell. First is primitive, then body centered, then face centered. Next is tetragonal, simple primitive and body centered. Then hexagonal have edge centered primitive unit cell. Then orthorhombic, simple primitive, body centered, face centered and end centered. Then monoclinic, simple primitive and face centered. Then trigonal, simple primitive and triclinic. They have simple primitive unit cell. Next is crystal symmetry. Crystal symmetry is an important tool to discuss, to explain the stability of the crystal, because symmetry leads to stability. And the law of symmetry states that the crystal of a particular substance always possesses the same element of symmetry. Before discussing the crystal symmetry, there are few terms related to it, or symmetry elements. First is plane of symmetry, and second is center of symmetry. Their corresponding symmetry operations are, in first cases, reflection in plane, in second cases, inversion of all atom through the center, in third cases, axis of symmetry, one or more rotation about the axis, then improper axis of rotation, one or more rotation followed by reflection in a plane perpendicular to the rotation axis, and then axis of inversion, one or more repetition of the rotation followed by inversion through the centers. So these are the symmetry elements. The symmetry of crystal depends upon these 5 symmetry elements. These are the examples of symmetry elements. First are plane of symmetry. For example, in plane of symmetry, the plane divided molecules in 2 halves. First is hydrogen. Hydrogen have 2 types of planes. One is horizontal plane and second is vertical plane. And water molecule have 2 vertical planes. Next is center of symmetry. In center of symmetry, an imaginary point is considered at the center of the molecule, and then a line is drawn through that points. If we get the same atom in opposite direction, then the molecule have center of symmetry. For example, N2O5 have center of symmetry. Next is axis of symmetry. In axis of symmetry, an imaginary axis is passed through the center of the molecules, and after rotation they give equivalent configuration. Okay? Equivalent configuration. So these are the examples of center of symmetry, axis of symmetry. Symmetry element in a cubic crystal. As we know, cubic is the most symmetric crystal, and there are 23 symmetry element in cubic crystal. First is rectangular plane of symmetry, then diagonal plane of symmetry, axis of 4-fold symmetry, and axis of 3-fold symmetry, and axis of 2-fold symmetry, and then center of symmetry. In designation of planes, the law of rotational indices have great importance. According to this law, the intercept OL, OM and OK of a crystal are made up of unit cell axes. Miller extended these ideas and gave more accurate explanation to designate crystal lattice. According to Miller indices are reciprocal of intercept. Miller indices give the direction of planes. It is always integer value, not a fractional value. Plane is never considered on the origins. These are the examples of how to calculate Miller indices. First point is to convert intercept into to take reciprocal of intersect and then convert it into integer value. Then diffraction of a X-ray by crystal. In 1912, Maxwell found that the distance between crystal lattice, distance between atoms of a crystal are of same order as that of wavelength of X-rays. Then they concluded that when X-rays passes through the crystal, then crystal act as a diffraction grating. Act as a diffraction grating. Then Maxwell extended these observations and gave a law, Bragg's law of X-rays. According to Maxwell, when X-ray pass through a crystal, then the atoms in the path of the X-rays scattered radiation, act as a scattering center and produce secondary radiations. So Bragg's gave a equation that is 2d sin theta is equal to n lambda, where d is the interplanar distance between the crystal and lambda is the wavelength of X-ray. This equation is valid only for X-rays and not applicable for any other electromagnetic radiation such as UV visible or visible radiation. With the help of this equation, crystalline, we can explain the structure of every crystalline solids. Thank you.